In question number 16, we are given an inclined plane whose angle with the horizontal is 37 degrees. A block having mass 2 kilograms is placed on top of the inclined plane, and there is a constant force of 20 newtons which is applied to the block for a time of 1 second, and this force acts in a direction parallel to the inclined plane. Now, in a time delta t of 1 second, if the block moves by a displacement of x up the plane, then obviously the work done by the 20 Newton force is going to be 20 newtons multiplied by x. And in part A, we are supposed to show that this work cannot exceed 40 joules. So probably what this means is the work done by the 20 Newton force, the maximum possible work is 40 joules. So the problem reduces to finding what is the maximum possible work by this force. Now, if we draw the forces acting on the block, the other forces, so the weight of the block which acts in the downward direction, that is given to be 20 newtons. Actually it's 2 kilograms multiplied by g, and g is supposed to be 10 meters per second square in the problem, so you get 20 newtons is the weight. And let's resolve this weight into a component down the plane, which is going to be 20 multiplied by sine of 37 degrees, which of course turns out to be 12 newtons, and the component which is normal to the plane is 20 multiplied by cos of 37 degrees, and that turns out to be 16 newtons. And finally, there may be a frictional force acting in this direction, assuming that the block slides upwards, and this frictional force will be the frictional coefficient mu multiplied by the normal reaction. Of course, the normal reaction, which I should actually write first, exerted by the inclined plane on the block, has to balance the normal component of the weight. So the normal reaction N1 has to be 16 newtons, and therefore mu multiplied by 16 newtons will be the frictional force. Notice that we assume that the block is moving up the plane like that because we do want to maximize the work done by 20 newtons. So if the block moves down the plane, 20 newtons will do negative work. On the other hand, if it moves up the plane, 20 newtons does positive work. So moving down the plane is out of question. And since we assume that the block moves up the plane, the frictional force is going to be down the plane. Now let's return to our question. Remember, the work done by the 20 Newton force is 20 Newton multiplied by x, and to maximize this work, it is clear that x has to be maximized. Now if you look at the FBD, clearly the displacement of the block up the plane in a fixed time interval of 1 second is dictated by this 20 Newton force which is up the plane, this 12 Newton force which is down the plane, and these are fixed, you can't do anything to them, but it is this force which plays an important role. For example, you consider a case where mu is large and mu is small. If I compare these two cases, clearly the block in the same time interval of 1 second will move up by a larger distance, so x will be large if mu is small. There's less friction, the block moves more easily up the plane, and that would result in larger x. And remember, we want to maximize x, so x would be maximum provided that mu has the least possible value, and that we assume a hypothetical value of mu equal to 0. So in other words, the 20 Newton force will do the maximum amount of work if the plane is frictionless. So basically we have to now find the distance x by which the block moves up the plane in case the plane is frictionless. For that, in the FBD of the block, we draw the acceleration, which is in this direction, and we're doing part A, we apply sigma f is equal to ma in a direction up the plane, and let's see what we get. There is a 20 Newton force up the plane, it's positive, minus 12 newtons, and of course mu multiplied by 60 Newton, I can just remove it because mu is equal to 0, the plane is frictionless. So I've got the net force 20 minus 12 Newton, and that's the mass times acceleration. So mass is 2 kilograms and acceleration is a. Now this implies that a is equal to 4 meters per second square, and the direction of the acceleration is of course up the plane. So clearly the block moves with UALM up the plane, and the acceleration is 4 meters per second square. Remember, we want to find the distance by which the block moves up. The displacement of the block up the plane is given by S is equal to ut plus half at square. In this case, since the block moves up the plane, it doesn't reverse its direction. We just want to find the displacement of the block up the plane. So that's going to be 0, assuming the block starts from rest, plus half multiplied by a is 4 into the time is 1 second, 1 square, so I've got 2 meters. So in a time interval of 1 second, the block moves up the plane by x equal to 2 meters, and therefore we know that the work done by the 20 Newton force, the maximum work done, is going to be 20 newtons multiplied by 2 meters, and that's of course 40 joules. And in the case that friction is absent, we get a work done of 40 joules. Obviously, if friction is present, that would mean that mu is not equal to 0. So the block, it would not move so easily up the plane, and that would mean that the displacement up the plane would be less than 2 meters, and you would get work of less than 40 joules. So that means that the maximum work possible is 40 joules, and the work would never ever exceed 40 joules. Now in the next part, that is part B, we have to find how much is the work done by gravity, assuming that there's no friction and the block moves up as described in part A, up the plane by 1 meter. So just to describe the situation, see, the inclined plane is this angle is 37 degrees, the block is over here, and the block moves up by a distance of 2 meters. And of course, when we are calculating the work done by gravity, it's the vertical displacement of the block which becomes important. So I just take the component of 2 meters is going to be 2 multiplied by sine of 37 degrees, which is 2 multiplied by 0.6, which is 1.2 meters. In other words, the block has risen by 1.2 meters in the given time interval of 1 second. Now there are several methods to find the work done by gravity, which is what is asked in the question. So for example, the work done by gravity can be calculated using the formula minus F bar dot S bar. The other way to find the work done by gravity is by using the potential energy concept. The work done by gravity would be the negative of the change in the gravitational potential energy of the block, and I will demonstrate the solution by this second method. So for that I must first find what is the change in the gravitational potential energy of the block during this given time interval of 1 second. So that's clearly mass of the block into g multiplied by delta H of the cm of the block. Now the mass of the block is 2 kilograms. G is assumed in the problem to be 10 meters per second square, and the cm rises by 1.2 meters, so 1.2. Now if I calculate this, I get 24 joules is the change in the potential energy of the block because of gravity, and I put it over here, so there is a minus sign. Obviously the work done by gravity is going to be minus 24 joules. Now the minus sign is to be expected. Remember, gravity acts in the downward direction, while the vertical component of the block's displacement is in the upward direction. They are oppositely directed, so obviously the work done by gravity must be negative. And in part C, we must now find the kinetic energy of the block at the instant the force ceases to act, that is after the passing of 1 second. There are several ways again to solve this problem. For example, one could find what is the final speed of the block using v square is equal to u square plus twice as. Remember, a has been calculated in the first sub question, and then of course one can say the final kinetic energy of the block is half mv square. That's one way to do it. The other way is to apply either the work energy principle or this conservation of energy to the block. I'll do it that way. So what you get is the work done by the 20 Newton force equals the change in the kinetic energy of the block plus the change in the potential energy. Now the work done by the 20 Newton force has been calculated in part A to be 40 joules. The change in the kinetic energy is half into m into v square. That is to say, it's the final kinetic energy of the block which we want to calculate minus the original kinetic energy is equal to 0, and the change in the potential energy of the block has been calculated in part B. It's over here, so just substitute 24 joules. Now this implies that the final kinetic energy of the block at the end of the 1 second journey is 16 joules. Now there are one or two points to note. One point is, on the left hand side you have taken the work done by only the 20 Newton force. We did not consider the work done by gravity on the left hand side because it is already included in the change in the potential energy term over here. Remember, the change in the potential energy is the negative of the work done by gravity. Secondly, remember the inclined plane. If you go to the earlier part of the problem, you look at this particular force. The inclined plane exerts a force of 16 newtons, a normal reaction on the plane, and this force is also not included in the work done on the left hand side over here. Now the reason is that the normal reaction of the plane on the block does 0 work. See, the normal reaction acts in this direction, whereas the displacement of the block is in that direction. This angle being 90 degrees, the normal reaction does 0 work, so it's not included on the left hand side. And finally, the frictional force does 0 work because the friction itself is equal to 0, and therefore frictional work is not included on the left hand side. The final answer is the kinetic energy of the block after 1 second is 16 joules.